Hi, this is Mrs. Jackson, and this is Chapter 1, Section 1, Part 6. And in this video, we're going to be talking about 4 common functions. We call these parent functions, and we're going to be looking at their graphs and key features of the graphs. Before I get into the specifics of these 4 functions, let me first say that this course, Algebra 2, really should be titled Functions. In addition to these 4, as we progress through the chapters, we're going to be studying probably about 7 additional function types after these 4. So that's really the heart and soul of the course, is to look at all these different function types. And the idea behind a parent function is that for each type, there is a parent, the most basic form of that type. And all other functions that look like that can really be described as transformations to that parent. So that's really the 10,000-foot view of the course. So anyway, let's get started. The first function we're going to be looking at is one that you're very familiar with. It's called a linear function. The parent of all linear functions, the most basic form, is y equals x in 2-variable equation style, and then if we wrote that in function style, it would be f of x equals x. You probably already know what this function looks like, but in all functions, it's a good idea just to put a few points down, and I like to pick some domain that are negative and a few values of domain that are positive. So if I one by one substitute in my chosen domain here, I would see that my output is exactly equal to my input. And once I have these points, ordered pairs, then I can graph them. So I'm going to go ahead and zoom in here. And I can graph negative 3, 3, negative 2, 2, negative 1, negative 1. And you can see, oh, I missed my origin. Okay. And as you know, a line or linear function goes on infinitely in both directions, and we indicate that by the arrows. So in this parent function, our x-intercept, there is 1, and it is the origin, and our y-intercept is also the origin. If we use some of our new vocab here on features, we can identify the domain, the range, increasing, decreasing, these are all intervals, positive, and negative. So from the domain perspective, there is nothing limiting our inputs whatsoever. So we can go from negative infinity all the way to positive infinity. And of course we can't touch infinity, so those will be open on either end. I'm going to only write interval notation here in the interest of space. Likewise, our range is completely unlimited. So from an output perspective, we can go from negative infinity to positive infinity. Now, our increasing interval is those values of x that are going to cause a positive slope. And in the parent function of our linear function, the entire thing is positive. So if we write that interval, it would be exactly the same thing as the domain. And in this parent function, we have no decreasing interval, so this doesn't exist. And in terms of a positive interval, remember, we're looking at those values of x here that are going to create a positive output or an output greater than 0. And so only half of this portion is going to be above the 0 line. Remember, right here at 0, that's neutral. That's neither positive nor negative. So that's considered an open. However, all these other values here are in the positive. So we're going to go 0 with an opened, that's shown with a parentheses, and that's going to go all the way up to positive infinity, which we can't touch, so that would also be considered open. And likewise, the negative interval here is the portion of the graph that is below the output of 0. And so it's important. Now, one common mistake I will say is that a lot of people write this as 0 to negative infinity, and that's not correct, because remember, the first number has to be the smallest. So this is the minimum. So negative infinity would go first, and the maximum would be 0. All right, the next most common function we're going to be talking about, in fact, all of chapter 2 is about this function. It's called a quadratic function, and in two variable equation style, the parent is y equals x squared, and in function notation, that would be f of x equals x squared. So if we made a little table of ordered pairs and picked a few negatives, and 0, a few positives. If we substitute negative 3 in and we square it, we get out a positive 9. Negative 2 squared is positive 4. Negative 1 squared is 1. 0 squared is 0. And we'll get the same exact thing on the positive side. All right, so if we graph those ordered pairs, negative 3, positive 9, negative 2, 4, negative 1, 1, we've got 0, 0, or the origin, and you'll have a mirror image on the other side. So this is called a quadratic function, and a quadratic function graph is called a parabola. And you can see, just looking at the ordered pairs, that it's completely symmetrical. And we call this green line here the line of symmetry. And if I asked you for the equation of that line, the equation of the y-axis is x equals 0. So the line of symmetry, the parent quadratic function, is x equals 0. Just like the linear function, we have only one x-intercept for this parent, and that's the origin. And the y-intercept is also the origin. So if we looked at our domain and range, all of our features, increasing, I'm going to abbreviate decreasing, and positive interval and negative interval. Our domain, again, is completely unlimited, so there's nothing stopping me from going all the way down to negative infinity and all the way up to positive infinity. Completely unlimited, and likewise, the range will continue to grow. However, you can see that on our parent quadratic function, we're never going below the 0 line, because when we square a negative number, it becomes positive. So our range, the minimum, is 0, and we can touch it. So that's going to be considered a closed circle at 0, and then it'll just grow all the way up to positive infinity, which we can't touch, so that'll be parentheses. And then for our increasing interval, that is the positive slope. So the right side of this symmetrical function is going to be giving us that increasing interval, and on either side at this point right here at the bottom of the hill, we're at rest. We're not increasing or decreasing. So we start at 0 and we increase all the way up to infinity. And on the decreasing interval, the minimum would be negative infinity. I know that's hard to see, but remember, intervals are always the x values here except for the range. So if I kept going all the way and over here to negative infinity, that would yield the minimum over here. So we're at negative infinity and we stop decreasing at 0. And then positive, you can see here that the entire parent function is positive. It's all above the 0 line. The only problem here is that this vertex, this point at the origin, is neither positive nor negative. It's neutral. So it may at first be a little bit awkward to see, but we actually have to describe two positive intervals here because we have to break out that 0 point. So the first positive interval is that one on the left. It begins at negative infinity and ends at 0. And the second one begins at 0 and goes to positive infinity. By splitting this out in two with the parentheses, I'm excluding that 0 point. That's what's happening here. And then finally, negative interval, there is no negative interval. The whole thing is above the 0 line. The third parent function we're going to talk about is the absolute value function. And the equation is y equals the absolute value of x. And in function form, f of x equals the absolute value of x. So if we made ourselves a table to get a feel for what this function looks like, if I put in a negative 3 here for my x, if I put that in there, of course the absolute value turns a positive. So I'm going to get 3 out. Likewise, negative 2 will become 2, negative 1 becomes 1, and 0 becomes itself. And then if I put in the positive numbers, only the positive comes out. So the definition of absolute value, the true definition, is that if you take the absolute value of a number, you're finding its distance to the origin on a number line. And distance is always positive. That's why everything coming out of an absolute value symbol is positive. So if I graph those ordered pairs, it looks kind of like the quadratic. Only it's got pieces of linear looking functions here. So you get a V, and it'll go on infinitely in both directions. And for the parent absolute value function, its vertex is at the origin. And kind of like the quadratic, it's symmetrical. So it has a line of symmetry here. And the equation of the line of symmetry is the y-axis, and that is described as x equals 0. And likewise, the x-intercept is the origin, and the y-intercept is the origin. Because its shape looks so much like a quadratic, its key features are almost identical, if not identical. So domain, range, increasing, decreasing, positive, negative. Nothing limiting the domain, so it's all real numbers. And the range, again, is being forced into the positive. So we have our minimum is 0, and our maximum is infinity, and we can touch that 0. It's on the graph, so that would be a closed circle. The increasing is going to be the same thing as the quadratic. It starts to increase in a positive slope at 0 with an open circle there, and it starts to decrease at negative infinity, going up to 0. And the positive, again, the whole function is above the x-axis. However, because of that vertex there at the origin, and that is neither considered positive nor negative, we have to split this up into two. So, and by doing so, we're excluding the 0. Again, that might be a little tricky at first, but by splitting that up into 2, we're excluding 0, and then there is no negative interval. All right, the last most common function we're going to talk about in this chapter is called the constant function, and its equation is y equals 1 or f of x equals 1. So to get a feel for that, it might seem trivial, but I think it's a really good skill to be able to kind of map out and create your own function. If I put in a -3 here into this function, no matter what, this function is going to equal 1 out. So that hence the name constant. So when I graph this, of course, doesn't matter what you put in, you're getting 1 out. And the graph then creates a horizontal line. Oh, I don't like the look of that. The graph will create a horizontal line infinitely in both directions. So you can see here from the graph, we have no x-intercept. We're not crossing the x-axis at all, and the y-intercept is going to be at y equals 1, or in point form would be 0, 1. The domain is completely unlimited. And the range is 1. So it really doesn't have a minimum or maximum. It's always going to be a 1 out. In terms of increasing, there is none. There is no interval where that function is increasing, and there is no interval where that function is decreasing. In terms of the positive interval, the entire thing is above the 0. So all real numbers. And there is no negative interval here because the whole thing is above the 0 line. Now, one thing to note, you might be curious as to why not have a constant function that instead of being a horizontal line, why not a vertical line? Well, that would not be a function at all. So if I drew some kind of vertical line here, you could see that for any given value of x, there would be an infinite values of y. And so that wouldn't be a function at all. So that's why we wouldn't even talk about that. Anyway, these are the most common parent functions that are introduced in Chapter 1, and we're going to be looking at many, many other types of functions going forward in the course. I hope this helps.